Generic programming or generative programming is a programming style, is a technique to produce code which can be reused. It can be reused as often as you want and will always work. So there are two things that the software engineers have been trying to do forever. It's like getting someone to write a piece of code that will be used by everybody else. You write it once, everybody uses it. It doesn't work like this almost never, because there's some implementation details or something that is not compliant with something else, so it's difficult to get it. So reusing components, also components can be very complicated, difficult to reuse, etc. But this is one of the dreams. And the other dreams is unifying interfaces. So if I have to sort a sequence of elements, I just want to call sort a sequence of elements. I don't want to do sort this, sort that. You probably are familiar with the BLAS interfaces for matrix multiplication. It has SGEM, DGEM, ZGEM, what else? Other CGEM, whatever, right? And plus it takes like an enormous number of arguments, like I think six or eight arguments. That's bad API, right? That's right there. It's a bad API. First of all, you have different functions to do basically the same thing conceptually, different names, plus many, many arguments. This is also something that is, a function should always take like 3 arguments at most, 4 if you really cannot avoid it, right? It should always work toward getting short argument list, a single name for doing everything. That is one of the dreams, because that becomes easy to remember. Maybe you are so used to DGEM that you know what the arguments are and you remember exactly how to pass them. But otherwise, you have to go to the manual, make a couple of errors, try to find out why things doesn't work. So unifying interface is one, and the other one is reusing the code. I want to use code. Let's look at that Python function there. It's implementing a reduction. A reduction is a common pattern, right? You go through the elements of a sequence, and you collect, you, for instance, do a sum of these elements. So here you get a reduction with the sum. Right? So I'm passing a sequence, an initial value, and I accumulate over this initial value the element in the sequence, and I return that value back. This is a very generic code. It works with whatever sequence allows you to iterate on. It works with any initial value as long as you can convert to it. And it simply works. So whenever you have to do a reduction of something, you just call this function and it will work. Problem with this is that there is a third dream that software engineers always wanted to have, which is code efficiency. This Python version is not efficient at all. Why? Because it's known at runtime what the sequence is, how to access elements, what type it is, also the initial. There is actually a Nash map somewhere that says, oh, sequence now is an array or is a list. And these prevent the code to be actually optimized at runtime. So efficiency is the other one. And those are conflicting requirements. I skip this one for now. There are 2 concepts in generic programming. One is algorithm lifting, which means take a piece of code that does something and generalize it. Remove constraints on that code. As much as the performance is not affected. Give you an example. This is a C implementation of an inner product over integers. You might wonder why someone wants to do an inner product over integers. Of course, a computer scientist. That's the only guy who can do something like this. But, that's the function you're working on. It takes 2 pointers to the beginning of the end of the input region and the starting point of the other vector. It has an init value, an initial value, which is also an integer, and you have a for loop that goes from the beginning to the end, and simply compute star begin times star end. So dereference these pointers, marches on the data, accumulate the value back. And this is the inner product. This function is not very useful unless the only thing you have to do is this one. But if I have to do iterating over a pointer of floating point numbers, I don't know who wants to do that. Someone might want to do that. And then you have to write another function. Now, in C++, you can actually do it because they overload resolution, which is the float pointers, and you go to the float pointer. In C, you have to put the different names in the function, or Fortran for sure. So that doesn't work very well. You have to write a lot of code. So instead, why don't you make it into a template? It takes an input something, an input to something else, some type, and some initial value or some other kind. And then the inner product will be basically exactly the same code as before. We have we use the star operator to dereference anyway. And so we require that the input IT1 and input IT2 have these requirements that have to support the star operation to access an element and have to support the ++ operator to advance to the next element. And also has to support the comparison operator. And those are iterators. This is just a forward iterator in the standard library. So and this is the code. So first of all, we put this thing into a template, and now it works with anything that can iterate over data and can do these operations. Plus, we transform the plus equal into the plus, into init equal init plus. And the reason is that it's more usually people implement the plus operator, not the plus equal, so it's slightly more general to get the plus operator instead of a plus equal. Just at least this is actually the STL code. This is the standard template library code. We will go back later on why we need those weird names there. Why the STL has all __ first one and all these weird names. We'll come to it later if we want to keep going on these things. The other mechanism in generic programming, apart from lifting, so generalizing the algorithm, make it more general, make the code so general that you can simply instantiate it and having working for different data types and different cases, so reusing the component effectively. The other one is the specialization, which is pushing the lifting even more. So lifting stops when the performance is affected. If my code becomes inefficient for some reason because my operations are too general, then I might want to do something more. I want to specialize in this case. So I have a sort function that takes some array and just do something to sort the thing. And I want to sort a vector of chars and a vector of integers. This will work as long as that thing sorts a vector of elements, that thing will work. But it might be not as efficient, for instance, for sorting a vector of chars. And why is that? The chars is only 8 bits long. If I have 100 million chars, sorting using quicksort or any other comparison-based sorting is not going to be effective. It's better to use something like counting sort, like radix sort, etc. So you want to have a different algorithm and a nice animation in which you specialize your algorithm. You say, well, sort for a vector of characters, and I do there a special algorithm that I know will work for this guy. It will be like counting sorts or, radix. I don't know if you know these algorithms, doesn't matter. It's just different algorithms, different ways of sorting. So these are the two main mechanisms. So lifting, generalizing, make your functions templates instead of functions, and specialize to get efficient cases. Accidentally, this version for the chart can be added later on. The first version of my library is going to be slow for some cases, and then later on I push an update to the guys and say, update your code, I have a better implementation for you. This brings the idea of concepts. Concepts you might have heard about. It's a feature that people trying to get into the C++ standard but cannot make it somehow. It basically is the minimum number of requirements that a type has to satisfy in order to be used by a generic function. For instance, sorting in STL requires that you pass in mutable random access iterators. We will see what iterators are in a bit. It has to be less than comparable on the value type of that of those iterators. Iterators has a value type, which is the value which is pointing to, and it has to be less than comparable. And there is also a comparator can pass to the sorting algorithm that should take value types and return you a bool. And this is the requirements that your sorting algorithm asks you. So whatever you're passing to this STL sorting algorithm that has these operations, the code will compile and the code will run. What it will do is up to you. If you pass a vector, it will sort the vector. If you pass something weird that does these operations, we'll get some weird results. And the concepts are used to bridging components, bridging data structures, bridging algorithms. In the standard template library, you get the iterator concept, which is the bridging concept between data structures and algorithms. The algorithms are written just in terms of iterators. They don't know anything in principle about the container. The container exposes iterators. And so when you pass the iterators to the algorithm will work. But there is a total decoupling between data structures and algorithm. The algorithm is written, it's like you have a different language to write your algorithm. You write your algorithm using iterators. You provide a data structure that provides iterators. You can use the algorithms on those containers. And there is the iterator category, which is basically different concepts, which is the iterator, which has the star operation in the plus plus to advance it. We have input and output iterator. One can only read, the other one can always only write. And they provide a comparison with the difference. So it can tell you if two iterators are the same iterators or not, and can tell you, it can dereference, and it can advance also with the post increment. Now you have the bidirectional iterator that gives you also the minus operation, so you can go forward and backward. And you have the random access, which give you also comparisons and random access, offsetting, and difference. An algorithm which is written for a random access iterator is assumed to use all of this. So if you pass an iterator that doesn't have those things, if you pass an input iterator to something that requested the random access iterator, you get a compilation error. But because the input iterator doesn't match the concept needed by the algorithm needs a random access iterator. Just to show you before going lunch, this example is the actual standard template library code for implementing the minimum and the maximum functions. And the minimum is like a function that takes two arguments, A and B, which are templates, and it has a checking here that says, oh, check that this guy is less than comparable concept. This is an internal GCC implementation thing. and then says if B less than A, return B, or otherwise return A, and max is the other one. And it says the same concept, less than comparable, because instead of doing B less than A, it does A less than B. So the max and the min has the same set of requirements, right? The less than comparable. Now, there are things here like, why is it that, oh, I see a macro here. Come on. Everybody told you to not use macros, and these guys in the standard library, they're using macros. They're cheating, right? And there are these weird names, underscores, and, well, 3 minutes. I think it's interesting. Why you want to use macros? Oh, because you want to write generic code. You want the code to compile. In case of C++ 14, for instance, you want this to be const expert. I want to compile it. You want to have the value at compile time if possible, while C++ 11 cannot do it. So you just put a macro there that is available only in C++ 14. Right? And this is okay. You write a single function to handle different standards. So the STL guys who wrote this thing, you say, I don't care about the good practices here, I put a macro. And it's okay, it's just a macro defined by the compiler. If you happen to define by chance in your program that string, you got in trouble. And this is why the names are so strange. It's not simply C++ 14 const expert, because you might be defining the same macro in your code. So they use weird names that are very difficult for you to use. It would never come to your mind to use double underscores for an argument. If you define a macro which is double underscore B in your program, then you call this thing will not compile because B will be substituted with whatever macro is. So they try to get names that are difficult to mess up with. Again, the same minimum requirements on the function, and this implement the protections that we have seen before, like a static assert, right? So they do the same. And what about comments? Do you think this code can be commented? Should it be commented? Does it need comments or not? No, right? Very easy. Look at the comments that is in the standard library. A huge comment. There are two reasons why there be comments. First of all, the top one are actually Doxygen comments. So it is to generate automatic documentation of your code. So you run Doxygen on this, and it will give you like a web page or a PDF with a description of the function. And second, there might be something that is subtle that you wouldn't think of, but is actually quite important. The second sentence is, this is a simple classic generic implementation. It will work on temporary expressions since they are only evaluated once, unlike preprocessor macro. Cool, isn't it? So many people, I guess everyone, right? Everyone has done it, has to do a min and a max in their program. They define a macro, define min A, B, and if A less than B, then A, otherwise B. That is a macro expansion, and this is dangerous. In fact, if you have defined this macro defined and you pass it a function call there, it will be text substituted. Suppose you're passing f minimum between f of A and g of B. It will become in the code, if f of A less than g of B, then f of A, otherwise g of B. The function will be evaluated twice. One function will be evaluated twice, which means not only performance issues, because you're calling a function, maybe not aligning, but if the function happens to have side effects, you'll get in real dirty troubles. So in this case, if you use the STL, it's telling you this is way better than any macro you will write. First of all, it can be lined easily, and we'll evaluate the arguments only once because it's the caller that evaluates the arguments and not the macro itself, and not the function itself. And we can go to lunch if you have other questions. Yeah?
I have just one question regarding the concept. How do they help us before? Because you would get a compiler error anyway now.
So how is that concept helping, right? If you get a compiler error anyway. But the compiler error will be cleaner if you know that this type is not satisfying those conditions, instead of getting an error like, oh, this type, I cannot find these functions for some reason. I cannot increment this, which is the same thing, right? But you get the error earlier, and it's a better looking error message. If you are developing generic library very deeply, very deep, so with many abstraction layers, concepts doesn't help you that much. It's difficult to catch very early on errors because you don't even know at that point what are the concepts involved later on. So concepts gives you error messages early, and if we had concept in C++, it will simplify our life a lot. But still, the error messages might not be as beautiful as we would like. Okay, let's go to lunch then.